Okay, so 16.1 is on vector fields, and they act a lot like slope fields in that, it's basically just an equation telling you what the vector behaves at for a certain point, and it creates this field of vectors. So hopefully you're able to read through the PowerPoint presentation on that. We'll be using the idea of vector field throughout, so I'll be covering it as I use it. Okay, but I just felt that it was best to have you kind of read it on your own, since it was just defining that one concept for basically the whole section. And there's not much math involved there. Okay, so let's jump into 16.2 today, and we're going to talk about a line integral. What are line integrals? 16.2. Okay, line integrals. Okay, so in Calc 2, okay, we defined arc length given by parametric equations. Okay, so arc length as L equals a to b, integral of a to b, of the square root of dx dt squared plus dy dt squared. Okay, dt. Okay, so the derivative of x with respect to t squared, derivative of y with respect to t squared on dt. Okay, integrating over a curve C gives us something called a line integral. Okay, and really it's really a curve integral, but it's called a line integral. Okay, it's a curvy line. Okay, it should really probably be called a curve integral. So the idea here is that if we have in 3 space, okay, this curve, okay, we can find the integral under this curve. Okay, so think of it as, okay, think of it as maybe as a flag waving. Okay, but we're finding the integral under this curve. Okay, so we have this kind of this line. Okay, this function in 3 space. Oops. So we have this kind of function in 3 space, and then everything underneath it, okay, we're going to integrate. Okay, and that's called a line integral. Okay. So, okay, so this thing here is f of x, y, and then we call a C kind of like the domain or the projection of the curve onto the xy plane. So we will say that this guy here, okay, is C, curve C. It's just it's the same curve that we had above, but it's just being projected in the xy on the xy plane. Okay, so let's give a formal definition here. Okay, the integral of c, f of xy, okay, the integral of f of xy in 3 space, okay, over c, which is our domain. Think of it as our domain, okay, our line, in quotes, okay, and this is ds, okay, with respect to the, okay, with respect to that line, okay, ds, okay, with respect to that curve. You can think of it as back to the curve, okay, okay, ds is with respect to that curve c, okay, is equal to the integral from a to b of f of x of t. We're going to make sure this is parametrized. Y of t. Okay, so we're gonna take the integral of f of x xy. Can you not hear me? Oh, you can hear me? Okay, got it. Okay, good. Okay, so f of x t y t, okay, over the curve, okay, over the integral of the curve. So we're kind of integrating down with this piece of it, and we're integrating over, okay, with the next piece, which is just that arc length. Is basically the arc length. We're integrating down, okay, here, and we're integrating with respect to the arc length. So, and what was the arc length? The arc length was dx dt squared plus dy dt squared, okay, dt. Okay. Okay, so let's do an example here. Okay, example 1. Okay, evaluate the integral over c of 2 plus xy x squared y ds. Okay, so this is with respect to a curve. Think of it, when you see ds, think of it, it's with respect to a curve. Okay, we're just integrating with respect to a curve. With respect to an arc length. Okay, we're integrating with respect to an arc length. Okay, so, okay, and we're going to say where c okay, is the upper half of the circle, x squared plus y squared equals 1. Okay, so what's really happening here? Well, let's take a surface, okay? I don't know what this surface looks like, but we'll take this surface here, okay? And then, so what's happening with this thing here, I'm gonna redraw this, okay, is that we've got this kind of like half circle, right? And so there's gonna be this projection of this half circle, right? On this thing here. And what I want to do is I want to get the integration. It might look more like this. Okay. Because it's like kind of going to go down here. But we want to get the integration over the half circle. Okay, so we really don't have this piece of it. If you want to be completely accurate here, we don't have this. Okay, and we don't have this either. Okay, we don't have this. And get rid of that there too. Okay, and so what is it that we're really integrating here? Okay. Okay, is that we're integrating, okay, this surface here. Okay, and that's our line integral. It's this piece here. Okay, so we have this surface that dictates how high the integral goes, but then it goes all the way down and it forms a semicircle. Okay. Okay, so what we really just need to look at is what is C in this case. C is the half circle here. Okay, and so how would we parametrize a circle, or x and y, in terms of a circle? Well, x equals cosine t, and y equals sine t.
Wednesday night.
Okay, and so x is equal to cosine t and y is equal to sine t. Okay, so what's dx dt? Well, dx dt, I'm going to need that as well. Dx dt, or the derivative of x, is going to be negative sine t, and dy dt is equal to cosine t. Okay, so now I'm just going to plug this into my function here. It's over c, right? Over c, okay. And so this c is going to be parametrized, okay, so, and we have t now, it's going to be over t. We'll deal with c in a second. We're going to get this function here, which is 2 plus x squared y, but what was x? X was cosine t, and what was y? Y was sine t, okay, times the square root of negative sine t squared plus cosine t squared. Oh, okay, but I know what this is. This thing goes to 1, and the square root of 1 is 1, and this is with respect to t, dt. Okay. So this becomes over c. But what is this arc in terms of t? My variable here, t, well, x is the cosine of t. That's the angle, right? T is the angle. So we're going to say that t goes from 0 to pi, right? Doesn't it go from 0 to pi? Okay, and so 0 to pi of 2 plus cosine squared t sine t dt. Okay, awesome. That's good. Good, good. Okay. So now we're going to go split this up. 0 to pi of 2 dt plus 0 to pi of cosine squared t sine t dt. Okay, nice, nice, nice. So this is 2t from 0 to pi, which is 2 pi. Right? Okay, plus we're going to do a u sub on this. U is equal to cosine t. Du is equal to negative sine t dt. Okay, so negative du is equal to sine t dt. Okay, so stop. Okay, whatever. Okay, so we could change our limits if we want. It doesn't really matter. We could go back to t if we wanted to at the end. I may just go back to t at the end. We'll see. Okay, but what's this going to be? This is going to be negative u squared du. Okay, and so then I'm going to go, this is negative 1/3 u cubed. Oops. Okay, and so I'm going to plug in what my u was. Okay, and I'm going to say negative 1/3. Okay, what was u? U was cosine t cubed, evaluated from 0 to pi. Okay. Okay, and that's going to be added to by 2 pi here. Okay, so this is going to be negative 1/3 times the cosine of pi cubed minus negative 1/3 times the cosine of 0. Oops, of 0 cubed. Okay, so the cosine of pi is negative 1. Negative 1 cubed is negative 1. Negative 1 times negative 1/3 is positive 1/3. Okay, the negative of a negative here, the minus of a minus, that's positive. 1/3 times the cosine of 0, cosine of 0 is 1. 1 times 1 is 1/3. So this becomes 2 pi plus 1/3 plus 1/3, or 2 pi plus 2/3. Okay, and that's our line integral. Okay, let's try another one of these. Okay, number 2. Evaluate the line integral over C of 2x ds, okay, so where C consists of the arc C1 of the parabola y equals x squared from 0, 0 to 1, 1. And C2, x equals 1, from 1, 1 to 1, 2. Okay, so we're going to look at our arc length here. Okay, or look at our line integral. What the heck's going on here? Okay, so from 0, 0 to 1, 1, we're getting C1, which is the parabola. Okay, so this parabola here. So that's C1. And then we're going to get a vertical line, okay, from 1, 1 to 1, 2. So we go from this parabola, okay, into this vertical line. Okay, so this thing here is C2. Okay. So we kind of think of T as the parameter that's sending us from 0, 0 to 1, 1 along this trajectory, and then from 1, 1 to 1, 2 along this trajectory. Okay, so for y equals x squared, okay, y prime is equal to 2x. Okay, actually, let's not do that. Let's parameterize this first. Okay, so if I wanted to parameterize this in terms of t, I could just say, hey, let t equal x, right? X equal t. Okay, then what is y? Then y is equal to t squared. Okay, so then what's x prime? X prime would be equal to 1 dt, right? We're taking the derivative with respect to t. Remember, this is now x of t. We let equal to t, right? And this is y of t. So x prime of t is equal to 1. Y prime of t is equal to 2t. Okay, cool. Okay, and so we're going to kind of break this up into 2 line intervals. And we're going to say, when t goes from 0 to 1, okay, why is that? When t goes from 0 to 1, well, what are we getting here? Are we getting this parabola in parametric form? Oh yeah, then what does this tell me? This tells me that x is, when x is 0, y is 0. Okay, that makes sense. It also tells me that when x is 1, y is 1. Oh, that works. When t is 0, we get 0, 0. Okay, when t equals 0, L there. And we get 1, 1 when t equals 1. Okay, so it's working. Okay, so we parameterized it correctly. And now we just want to find, well, what's the arc length of this piece? The arc length from 0 to 1 of, okay, of what? Of 2x. Okay, 2x. But what was, well, let's just put it in 2x. Okay, ds, right? ds. Okay, so, okay, from 0 to 1 plus, okay, from 1 to 2, okay, 1 to 2 of 2x ds. Okay, ds. So from 0 to 1, 1 to 2. Okay, so but we're going to end up with different x's and basically t is going to represent something different in both of these. So for the first one, okay, it's going to go from 0 to 1, and then this is x. Well, what was x? X was t, right? Because we want to turn this into dt. So x is t, so this is 2t times the square root of, I mean, maybe, I don't know, because let me just remember what the formula was. It was k over c, right, and from a to b of f of x of t, y of t, right, square root of dx dt squared plus dy dt squared, dt, right? So just keep that in mind. This is what we're trying to look for both of these pieces. So this is 2x, but again, what is this in terms, what is this terms of x of t? Turn x into x of t, well, that's t. So this is 2t, right? Times the square root of the derivative of x squared, well, that's just 1 squared, plus the derivative of y squared, well, that's 2t squared. Okay, and that's dt. Okay, nice. Okay, so now, what have we got? Well, we have, we need to deal with this guy here. How are we going to represent a vertical line? Okay, with respect to t. Okay, so, well, what is that line? That line, C2, okay, C2 is, we'll say we'll kind of put this on pause right here. Okay, for x equals 1. That's the line. Okay, x equals 1. Okay, from what? From okay, stop, go away. Okay, from 1, 1 to 1, 2. Okay, so we know that the x is always the same, right? The x is always 1. Okay, however, what is the y value going to be? What's the x is always the same, but the y is what's varying here, right? And it varies based on what position we're at, and we could call that position t, right? So I mean, think of it this way: like if t is 1, then what's my point? My point is 1, 1. If t is 2, then what's my point? 1, 2. Right? So it does work. Okay, so what's x prime here? X prime is 0. What's y prime? Y prime is 1, right? So if we think about it like this, then we're going to add 1 to 2 of 2x. But what is x? What's the function of x? We'll call this x of t. Well, isn't that just 1? Yeah, it's just 2 times 1. That's the function. That's the line that we're integrating under. Okay, and in this case, it is a line. No quotes. Okay, the line that we're integrating under. Okay, and okay, that line, okay, that arc length is going to go from, okay, what? Is going to go from 0 squared plus 1 squared. Okay, and so what is that arc length? Well, that arc length is just 1. Well, does that make sense? Does that make sense that the line x equals 1 would have an arc length of 1 from t equals 1 to t equals 2? Well, of course. What's the distance between those 2 points on a linear path? What's the distance between 1, 1 and 2, 1, right? Sorry, on 1, 2. 1, 2, what's the distance between these? Well, it's 1. That's the arc length. Okay, so the arc length is 1. Okay, that's the distance between these 2 points. Okay. So this is just going to be, let me mute everyone again. Okay. Okay, and so this one's going to be really easy to integrate. This one, maybe not so much, but we'll get there. Okay, so we have 0 to 1 of 2t square root of 1 plus 4t squared dt plus the integral from 1 to 2. Okay, so right, c1, c2. Okay, 1 to 2 of 2 dt. Okay, that's interesting. Okay, let's do a u sub on this guy here. So u is equal to 1 plus 4t squared. Okay, then du is equal to 8t dt. I'm going to divide by 4. Okay, divide by 4. So this is du over 4 is equal to 2t dt. Well, look at that. There's my integration factor right there. Okay, and so I get the integral, okay, of square root of u, right, du over 4. Okay, and this is u to the 1/2. So if I integrate this, this becomes 2/3 u to the 3/2 times 1/4, right? Okay, times 1/4. Okay, and then what was u in this case? U was 2/3 times 1 plus 4t squared. And this is just cancel that. That just becomes 1/6, right? So 1/6. Okay, and this is to the 3/2. Is that right? Yeah, 3/2. Okay, evaluated where? Evaluated from 0 to 1. Oh, okay. Okay, so let's see what we get here. So if I plug in 1, okay, if I plug in 1, I get 1/6 times, okay, 1 plus 4 to the 3/2 power minus 1/6 times 1 plus 0 to the 3/2. That's just 1. Okay, so this is going to be 5 to the 3/2 over 6 minus 1/6. Okay. Okay. And so this is going to be, well, I could, this 3/2 is really 5 radical 5. minus 1 over 6. Okay, so that's what I get for that one. Okay, and then what about this guy over here? So we integrated the first part. Now let's integrate the second part. Okay, so 1 to 2 of 2 dt. Well, that one's easy. That's just 2t from 1 to 2. And I'm going to plug in the 2. That's 2 times 2 minus plug in the 1. That's 2 times 1. That's just 2. 4 minus 2 is 2. So I'm going to add 2 here. Plus 2. And what I might do is just create a common denominator. This would be 2, which is 12 over 6. Okay. And so we're going to get 5 radical 5 plus 11 over 6. Okay, and I could leave it like that if I wanted to. Okay. Okay, good stuff. Good stuff. Okay, let's do an application of this. Okay, 3. A wire takes the shape of the semicircle x squared plus y squared equals 1, where y is greater than or equal to 0, okay, and is thicker near its base than near the top. Find the center of mass of the wire if the linear density at any point is proportional to its distance from the line y equals 1. Okay, I'll let you finish writing that down. I'm going to go get a drink of water. Okay, I'm back. Okay, so let's draw a picture here. See what's going on. Okay, so we have this wire, okay, in the shape of a semicircle. Okay. And then we have the line y equals 1. And it's saying that the thickness of the wire is proportional to the distance to the line y equals 1. Okay? So the way I'm going to write that, I'm going to say that rho of xy is equal to k, it's proportional to the distance that the y value is from 1. So what's the distance between 1 and the y value? Well, the y value is going to be less than 1. Well, I'm just going to go 1 minus y. So that'll give me a positive distance, because we know that on the unit circle, our y values are less than or equal to 1. Okay? So it's proportional to the distance from the line y equals 1. Okay. Nice. Okay. So what's x bar going to be? Okay. X bar is going to be 1 over m times the integral, okay, of this line integral, okay, of x rho xy ds. Okay, so for our x bar, we just plug in the function, the density function, and an x, and we divide by 1 over m. Okay, what about y bar? What's y bar? Well, that's 1 over m times y rho xy ds. And so this is a line integral, okay, over this as well. Okay, and so we want to know what's the center of mass of this wire. Okay, what is the center of mass of this wire? Well, it's pretty symmetric. So I mean, you could almost guess what the center of mass of the x value would be, right? Because this is the x direction. What would the center of mass of the x direction have to be if this was a semicircle? Okay, of radius 1. Well, if you guessed that it's at 0, you would be right. Think of a wire here, and think of it balancing. Where would the balancing point be of this wire? Well, since it only has to deal with the x, or since the density only has to deal with the y value, and it's symmetric, the shape is symmetric, then it's going to be more dense, right, the further away we are, but it's going to be symmetric. We'll use thickness of the line as density. Okay, it's kind of like, oh, okay, so it gets denser, right? The further away from that line I get, the denser it gets. But on the other side, it does the exact same thing. It gets denser the further away I go from this line, right? So it's proportional. Okay, right? So it can get more or less. It really doesn't matter. It just depends on what k is. If k is a number bigger than 1, then it's going to get more dense. If it's a number less than 1, it'll get less dense. It'll be an inverse relationship, but again, it really doesn't matter if we're scaling up or scaling down. But again, you can see that the balancing point for x, at least, should be easy to see that the x equals 0. X bar should equal 0. Equal 0? I don't know. Okay, so let's take a look at this. Let's look at what m is. What's m? M is just the line integral of rho of xy ds. Okay, so how are we going to parametrize this thing? Well, since it's the unit circle, let's just parametrize it with the respect to the unit circle, right? Wouldn't x equal cosine t and y equals sine t, right? Just like we did before. Okay, and what's t going from? T is going from, okay, with t going from 0 to pi. Okay, just like we had done before. Okay, so what is this function? Well, this function is k times 1 minus y. Okay. Okay. And so what's y in this case? Well, I'll just say ds. And, okay. At this point over c. Okay. But now we want to parameterize this. We want to put y in terms of t. So this is going to be k times 1 minus sine t dt, right? And then what's t going from? It's going from 0 to pi. Okay. And so now we want to just integrate this guy here. I'm going to pull the k out in front. And so this becomes t. Integrate sine, we get negative cosine, and so this is just going to be positive cosine, plus cosine of t, okay, and evaluated from 0 to pi. Okay, so yeah, front. And this thing is going to become k times pi plus the cosine of pi minus 0 plus the cosine of 0. Okay, and so what's the cosine of pi? Cosine of pi is negative 1, right? So this is pi minus 1, pi minus 1 minus 0, but what's the cosine of 0 is 1, so this is minus 1, pi minus 1 minus 1. Okay, times k. Okay, and so we're going to say this is k times pi minus 2. Okay, that's m. K times pi minus 2. Nice. Okay, so we've got what m was. Nice. Okay, so now.
Why are there two t's?
Why are there two?
Like 3 lines above, it's k and then t plus cosine t times t, or?
Oh, I'm sorry. No, it's just that.
Oh, okay, thank you.
Yeah. Okay. So, what is x bar? Then x bar is equal to, okay, 1 over m times the integral over c of x times, you know, rho xy. Okay, and so we're going to say, this is, okay, ds with respect to the arc length, okay, ds, okay, okay, and so we go 1 over m, okay, of, we're going to parameterize this, okay, parameterize this. Let's not just yet. Let's go x times k times 1 minus y, okay, ds. Okay, now let's parameterize this. This is 1 over m. Okay, times 0 to t. Put everything in terms of t. This is going to be cosine t times k times k. Maybe I'll just pull the k out in front. Okay, times 1 minus y, which is sine t. Okay, and then dt. Okay, I just want to check one thing real quick. Yeah, okay. So I don't want to skip steps. So I'm going to go back here. I forgot to do this on the last one. But if we take this guy and we do the arc, we went from the arc length to dt, right? So we went from this is a line integral. So, but what was this square root term here? I mean, if we do d prime of x, we get negative sine t, and then y prime we get cosine t, so we get negative sine t squared plus cosine squared t, which, you know, again, this thing goes to 1. So just keep in mind that I didn't really do any shenanigans, okay, but I did leave that out. So just know that this in this case, because we're using the unit circle, dx dt squared plus dy dt squared is equal to 1. Okay, so I just didn't want to leave that off. For whatever reason, I left it off in my notes on the first one. But we could do the same thing here. This is negative sine t squared plus cosine squared t, and that goes to 1. Okay, dt. Okay, so now let's see what we get. So k over m, 0 to, oh, this is not t, this is pi. Sorry, 0 to pi, okay, of cosine t minus cosine t sine t dt. Okay. Okay, and so we get k over m, and then this is going to be, what's this? Integrate this. This is negative sine t from 0 to pi. Okay, and then minus cosine t sine t. I'm going to use a u substitution on this. So if I let sine be u equals sine t, then du is equal to cosine t dt. Okay. So then this thing, okay, if I let this guy be my u and this thing be my du, okay, du. And if I integrate that, that's going to become u squared. So this is minus 1/2 u squared, right, from, and what was u? Sine t, right? So I can go to the next line here. So k over m, okay, this is minus sine t, okay, minus 1/2 u squared. Okay, but what is u? U is sine t, right? So this is, again, minus 1/2 sine squared t from 0 to pi. And this is negative sine t from 0 to pi. Well, what is this whole thing? What is the sine of pi? Well, it's 0. I mean, I could plug it all in, but you would see that everything's going to go to 0 here. Okay, so this is equal to negative sine pi plus sine 0. Okay, minus 1/2 sine squared of pi plus 1/2 sine squared of 0. But again, this whole thing goes to 0. Okay, and 0 times k over m is just 0, so the whole thing is 0, which we knew. Just by looking at this thing, we knew that it was going to be 0. Okay, what's more important is to find out, well, where is it on the y? Right, where is it on the y? And it should not be bigger than 1 or less than 0. Otherwise, we did something wrong. Right, where is it on the y-axis? Right, so we already know that x equals 0 is x bar. Okay, so but where is it on the y-axis here? Where is it? Is it here? Is it up here? Way up here? I don't know. I mean, it might get thicker as we go down, so you're kind of like balancing this thing. I don't know. Maybe it's pushed down there. Who knows? You know, maybe it's way below. So let's figure that out. Let's figure out where is the y bar. in this case. Okay, so y bar is equal to 1 over m times over c of y, okay, f of xy. So this is going to be rho of xy, okay, from or along that line integral ds. Okay, so we have y bar is equal to 1 over m times, let's turn everything into functions of sines and cosines. Okay, 0 to t, I get it again, 0 to pi of y. Well, what's y? It's sine t. And what's rho? What was rho? It was k times 1 minus y. But what was y? It was sine t. Okay. Okay, and then that's going to be times the square root of x prime of t squared plus y prime of t squared. But we already saw that this thing goes to 1 because it's the unit circle dt. Okay. Okay, so we get y bar is equal to 1 over m times, I could bring that k out in front, so k over m. Okay, and we get k sine 0 to pi of sine t minus sine squared t dt. Okay. Okay. So at this point, I'm going to plug in what the m was. What was the m here? The m was k over k times pi minus 2. Oh, okay, so those k's cancel out. Which is nice. So this just becomes 1 over pi minus 2. Okay, and then we're going to integrate these guys. Let me break it into two separate integrals. 0 to pi of sine t, okay, minus 0 to pi, this is dt, 0 to pi of sine squared t dt. Okay, so this is equal to 1 over pi minus 2. Okay, this thing is just going to be integrate, that's negative cosine t, right? So this is negative cosine t from 0 to pi. Okay. Minus. This thing I'm going to have to do a half angle identity on, right? So sine squared is, what is that? 1 plus cosine 2t over t. Is it sine or cosine? Is it plus or is it minus? I think it's minus. Yeah, so this is going to be 1 minus cosine 2t over 2, right? Okay, integrated from 0 to pi dt. Okay, so we've got is equal to 1 over pi minus 2. Okay, negative cosine t. Negative cosine t from 0 to pi minus. Okay, so this I'm going to break up into two different integrals as well. This is going to be minus, parentheses, the integral from 0 to pi of 1 over 2 dt minus the integral of 1/2 cosine 2t from 0 to pi dt. Okay. So let's clean this up a little bit. Well, let's do the integration, then we'll clean it all up. Okay, so the integration here is just going to be 1/2 t, or t over 2. So this is going to be t over 2 evaluated from 0 to pi. Right. Okay. Okay, what's this guy going to be? Okay, this guy, I'm going to do a u sub on him. Okay, minus this thing, minus, okay, let's do a u sub. U is equal to t, du is equal to dt, so du over 2 is equal to dt, right? So we know that at the very end, we're going to have to multiply by 1/2. We're already multiplying by 1/2, so we'd end up by multiplying by 1/4, right? So this is cosine of u now, okay? Cosine of u, so this is going to be 1/4 cosine u du. Okay, and so we want to integrate that. And so integrating that is just going to be 1/4 sine u, right? But what was u? U was 2t, so sub that back in. So 1/4 sine 2t evaluated from 0 to pi. Okay, and so yeah, so this thing is going to be equal to 1 over pi minus 2. Okay, this is going to be, let's start evaluating these now. Okay, plug in negative cosine of pi minus negative cosine of 0. Okay, what's that thing going to become? Well, the cosine of pi is -1. So this is negative of a -1, which is a positive 1. And then this is a negative of a negative, which is a positive, cosine of 0, which is 1. So that's a positive 1. So this thing just becomes 2. Okay, 2 what? 2 minus, okay, and let's evaluate this thing. Well, this thing just becomes pi over 2, right? Because it would be pi over 2 minus 0 over 2. 2 minus 0 over 2, which is just pi over 2. So that's minus pi over 2. Okay. And then what does this thing become? Well, this is going to be sine of 2 pi, which is 0. Okay. Not to be confused with the sine of 2 poc, which is not 0. Okay. So, okay, but the sine of 2 pi is 0 because that's just the sine of 0, which is also 0. So as everybody sees, this whole thing goes to 0. You're gone. Goodbye. See you later. Oh, look at that. And so we have this thing left over. Okay. So over pi minus 2. Well, that's kind of interesting. Okay. If I were to multiply both top and bottom by 2, then I could clear the fraction. And I would get 4 minus pi over 2 pi minus 4. That's kind of interesting. And that is just a number. And it should be some number between 0 and 1 if we did it correctly. So what is that approximately? Approximately, this thing is 4 minus pi, which is 0.858407. 0.858407. Okay, and then what's 2 pi minus 4? 2 pi, oops, clear that. 2 pi minus 4, okay, is, sorry, I can't read. It's clear. 2 times a pi equals that, minus 4 equals, there we go. okay, is 2.28318. Or 19, I guess. 19. Okay, so if we divide these two numbers together, okay, so let me just do this. 4 minus pi. I don't want to get a terrible amount of rounding error. Divided by 2 pi minus 4. Okay, it's about 0.376. Okay, roughly 0.376. Okay, or about 0.38. So yeah, is it between 0 and 1? Absolutely. Is it closer to 0 than 1? Yeah, it's about a third of the way up. So if we go back to the original drawing, we're about a third of the way up. So about right here is y bar. Okay, so this is y bar, and this is x bar, y bar. So that would be my center of mass would be right there. Okay, this is the point, x bar, y bar, which is the 0 and 0.376, right? That's my center of mass. So a lot of work to get to that center of mass, but it was worth it. Okay, so it's at 0, x bar, y bar is at 0 and 0.376. Good stuff there. Center of mass. Center of mass. Okay. Okay, definition. The line integral move this over. There we go. Okay, the line integral with respect to x okay is c f of xy dx, okay, which is equal to okay a to b of f of x of t y of t, okay, x prime of t dt. We're just saying let y be a constant and just integrate with respect to x. Okay, set y constant, integrate with respect to x. Okay, and so we would just let the derivative, if y is a constant, then the derivative of y is 0. So the distance is just x prime of t. Okay, because you get x prime of t squared and then you take the square root, right? So x prime of t squared plus 0 squared, right, is equal to x prime of t. Boom. There's your arc length. Okay. Okay. So the converse is true. The line integral with respect to y, okay, f of xy dy, okay, is equal to a to b of f of x of t, okay, y of t, okay, y prime t dt, right? We're going to parameterize that. Okay, so we can put all of this together and say, look, what happens when we take the integral with respect to x and the integral with respect to y? And we say, well, we have p of xy with respect to x, okay, plus if we end up with something with respect to x and then something with respect to y, and we call that q of xy with respect to y, then we could separate this. This is over this line integral, okay? But we have this separate one with respect to x and one with respect to y. Then this is equal to, okay, and we'll come back to this. We'll come back to this result. We're not going to prove it today. We're just going to use it. We'll prove it later on, okay? I'm just kind of setting up the things that we need to use so that we can pull them out a little bit later. Okay, so this is equal to, okay, the line integral over c of p of xy dx plus, okay, the line integral of c of q of xy dy. Okay, now if we were to parameterize this, right, q and t on q and, sorry, p and q on t, we could say, oh, well, this is from a to b of p of x of t, y of t, times x prime of t dt, plus the integral from a to b of q, sorry, this is q of x of t, y of t, y prime t dt. Okay, so again, we're just going to utilize this result, okay, a little bit later on, and we'll go back and prove it at that point. Okay, okay, recall also the vector representation of a line, of a line segment is given by r of t is equal to 1 minus t r naught plus t r sub 1, okay, 0 from 0 to, t goes from 0 to 1. Okay, so you're like, wait a second, I've seen that before. It was a very long time ago, but I've definitely seen it before, somewhere, okay? So, yes, you were tested on it as well. So, okay, we're going to use this as well. We're going to use all these ideas. And we're going to bring them all together. Okay, let's look at the next problem here. We have problem number 4. Evaluate. Okay, evaluate the line integral y squared dx plus x dy. Okay, where C is the line segment from -5, -3 to 0, 2. Okay. Interesting. So how are we going to parameterize this line segment? Right. So again, the line segment goes from in 2 space. So let's parameterize this thing in 2 space. Okay. So x and y. So we're going to say, okay, x and y. So it goes from -5, -3 to 0, 2. Right, so this line segment here. Okay, and so how would we parameterize this thing? Well, again, we would think of this as our vector, okay, R naught, and our vector R1, right? Okay, so our vector R naught and our vector R1 is creating this line segment. Where is R at 0? Well, it's at -5, -3. Well, where's R at 1? Well, the tip is at 0, 2. And so we're going to parameterize this thing and say, oh, okay, well, R of t is equal to 1 minus t times R naught plus t times R1. Oh, okay. So this is R of t is equal to, okay, well, what's R naught? Okay, 1 minus t. R naught is going to be the vector -5, -3. It's the vector from the origin to the point -5, -3. So -5 minus 0 is -5. -3 minus 0 is -3. So that's the vector R naught. Okay, plus t times R1. What's the vector R1? Well, that's 0, 2. The vector is 0, 2. Oh, okay. So now we're dealing with vectors. Okay, this is going to be good because we're going to do we're going to parameterize this thing using a vector, and then we're going to take the line integral, okay, over this parameterized function. Okay. So let's distribute here, shall we? Let's distribute this. Distribute this. We get 1 minus t times -5. Okay. Comma. 1 minus t times -3 plus 0t comma 2t. Okay. Nice. Let's distribute the -5. I'm going to get -5 plus 5t, comma. This is going to be -3 plus 3t, plus this is 0, comma 2t. Okay, so now let's add these together, add these vectors together. We get -5 plus 5t, comma, -3 plus 5t. Okay. And so that is, so what's x? What's x of t? Well, x of t in this case is this first component, which is -5 plus 5t. Okay. What's y of t? Y of t is the second component, which is -3 plus 5t. Okay. What's x prime? X prime is equal to 5. What's y prime? Y prime is equal to 5. Oh, okay. Nice, 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 nice. Okay. Good, 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 good. Okay. I'll put it, oh, whatever. That's fine. Okay. And again, what is t going from? T is going from, okay, t goes from 0 to 1. Okay, so keep that in mind. T goes from 0 to 1. Okay, so because we have it like so, okay, with one with respect to x and one with respect to y, and it's separated, okay, our previous equation said that when we do this, cy squared dx plus c, this is x dy, right? Yeah, x dy. We can break it up like this into two integrals, x dy. But then when we want to parameterize this, we're going to go from t, right? So this is 0 to 1, okay, of y squared. But what is y? Y is -3 plus 5t squared times y prime. But what is y prime? Well, y prime is 5, okay? So y prime is 5, and then it's dt. dt, okay. Nice, nice, nice. Okay, and then what's the next one? Plus 0 to 1 of x. Well, what is x? X is -5 plus 5t. And then this is going to be, let's see. So this is going to be with respect to y, so that's a y prime. So what was y prime? Well, y prime is 5. Okay, so this is x prime. This is y prime. Okay, because one was with respect to x, and one was with respect to y. Okay. Okay, so I'm gonna make this one integral. I'm gonna pull out the 5. Make this one integral. This is gonna be, I'm gonna square this out. This is gonna be 25 t squared. Okay, this is gonna be minus 30t. Okay, and then plus 9. Plus, this is gonna be 5t minus 5 dt, right? Okay, cool. Okay, so then this becomes 25t squared minus 25t plus 4, I'm thinking. Okay, and that's going to be integrated dt from 0 to 1. Let me just make sure that that's correct. I pulled out the 5, yes. So 25 squared, that's minus 30t plus 9, yes, like what I've done there. Plus 5t minus 5, okay, yes, okay. Let's see what happens. Okay, so what's this going to become? This is going to become 25 thirds t cubed minus, this is going to become 25 halves t squared plus 4t, evaluate from 0 to 1. Okay, so all that times 5. Okay, so plug in 1 and 0. Well, the 0 is just going to go away, right? So we should just be left with what the 1 is here. And the 1 is just going to be the coefficients of these fractions. This is 5 times 25 thirds minus 25 halves plus 4. Okay. So I got to change this to a common denominator of sixths. Okay, so sixths. So this is going to be multiplied top and bottom by 2. That's 56. Multiplied top and bottom by 3. That's 20. That's 75 sixths. Okay. Plus 4 times 5. Okay. Nice. Okay, so this is negative 25 sixths plus 4 times 5. Okay, so negative 25 sixths plus, well, change the 4 to sixths. That's 24 sixths. Oh, that's nice. So this is just 5 times negative 1 sixth, or negative 5 sixths. Boom, done. Okay, nice. Okay, let's take this up a one notch. Okay, take this up one notch, and let's talk about line integrals. Okay, line integrals in 3 dimensions. 3 dimensions now. Okay, so how does this work in 3 dimensions? Well, it's actually pretty similar to 2 dimensions. Okay, well, in 2 dimensions, what do we have? We had the line integral over c of f of xy, okay, ds was equal to, okay, a to b of f of x of t, y of t, okay, and the square root of x prime of t squared plus y prime of t squared dt, right? Okay, so what do you think this is going to be? F of x, y, z ds. Well, just add a third variable. That's it. So it's going to go from, okay, a to b of f of x of t, y of t, z of t, okay, square root of x prime of t squared plus y prime of t squared plus z prime of t squared dt. Okay. Okay, so let's do an example here with this. Okay, evaluate over C of y sine z ds, where C is the circular helix Okay, so now we're integrating over a space curve, basically. We're integrating over a space curve. Instead of a two-dimensional curve, we're integrating over a three-dimensional curve, which is a space curve. Okay, is the circular helix. Okay, x equals cosine t, y equals cosine t, and z is equal to t. Okay, for t going from 0 to 2 pi. Okay. So again, what does a circular helix look like? It looks like this, just for reference. Okay. Okay, kind of like a spring goes up. Okay. It could also go down. Okay, doesn't matter. Okay, there's your helix. Okay, and so what are we doing? We're integrating on this thing. Where are we integrating? We're integrating from 0 to 2 pi for t. So really, it's just one cycle of this thing that we're integrating on. I'm going to get rid of that. I don't like that drawing. I don't like this drawing either. Okay, so one cycle of this thing. Okay, so it'd be like right here. Okay. So one cycle. Okay. Actually, it wouldn't start there. Probably, it would probably start at 1.
Professor, I have a quick question.
Go ahead.
Where it says y is that supposed to be a cosine t as well?
Oh, no. No, it's a sine.
Okay. Oh.
Good catch. Thank you. Yeah, y is equal to sine t. Okay, so what are we doing? We're integrating over this thing here. Okay. Okay, but we're integrating with respect to that surface. That surface and is with respect to, okay, time, t time. Okay, so it's kind of a mess. I made it messy. I don't know. I am no artist, but whatever. Okay, so we got the circular helix, and think of it like this surface here. Okay, so now let's do this problem here. Okay, so I want to translate this. So what is this going to be? This is going to be from 0 to 2 pi of y. But what is y? Y is, again, sine t. Okay, and then sine of z. Well, what is z? Z is t. Okay, so sine t times sine t. Okay, times square root of what? Well, cosine t is negative sine t squared. What's sine? Sine is cosine t squared. And then this is plus z prime. Well, what's z prime? Z prime is just 1, right? So x prime is negative sine t, y prime is cosine t. Okay, and this is going to be 1 squared. Okay, and then that's dt. Okay, so what's this thing here? Well, this thing is going to be 1. So this is 1 plus 1 square root, which is just root 2. I can pull that root 2 all the way out in the front. So this is root 2 times the integral of 0 to 2 pi of sine squared t dt. Oh, okay. Well, we've seen sine squared before. How do we deal with that? Oh yeah, it's that half angle identity again. Okay, so this is 1 minus cosine 2t over 2. Okay, or 1/2 minus 1/2 cosine 2t from 0 to 2 pi, radical 2 on the outside. Okay, nice. Okay, I could actually factor out that 1/2 if I really wanted to. Just be radical 2 over 2. Okay, the integral of 1 is just t. So this is t evaluated from 0 to 2 pi. Okay, minus the integral of 0 to 2 pi of cosine 2t dt. Okay, and here we could do a u sub on this one. So this is just a u sub. So u is equal to 2t. Du is equal to 2 dt divided by 2. Okay, and we get 0 to 2 pi. Actually, I'm not going to do the limits. I'm going to plug it back in at the end. It's just easier for me to do that this way. So I mean, you could do the limits and then plug it in, and you'd have to reverse the order to get rid of negatives and stuff. I don't want to deal with that. I don't want to deal with the limits until the very end, because I know that this thing's just going to pretty much go to 0 anyway, because the integral of cosine is sine, and you plug in a 0 or 2 pi into a sine, they go away, it's 0. So this thing, again, just becomes d over 2. So this is going to be cosine of u, right? So the integral of cosine of u times d over 2 is just sine of u d over 2, right? Okay, so, but what was u? Well, sorry, what was u? This is, sorry, integral of that, this is just sine of u over 2, sorry, my bad. Okay, but what was u? U was 2t, so this is 1/2 sine 2t evaluated from 0 to 2 pi. Okay. And again, you just plug in your values here, and you're going to see that this is going to be the sine of 4 pi minus the sine of 0. Well, the sine of 4 pi, I'll work it out. 1/2 times the sine of 4 pi minus 1/2 times the sine of 0. Okay, well, that goes to 0, and that goes to 0. So the whole thing goes to 0. So this whole thing goes to 0. Okay, well, what's this thing here? This is 2 pi minus 0. So this is radical 2 over 2 times 2 pi minus 0, right? Minus 0, okay, for this thing. And so this is just becomes pi radical 2. That's it. So line integral. Okay, now let's discuss what happens when we take a line integral over a vector field. Okay, remember those vector fields? Okay. Okay, where we had we have some sort of vector field. Okay, a vector function r of t, right? So we have r of t vector function. Okay, so maybe this would be like t squared and t. right? This just tells us, hey, for a value of t, this is going to give me an x and a y, right? So no matter what I plug in for t, I can always find a vector, right? I can always find that vector. So say we had like this vector function here, okay? Then this is just going to create a vector field. Well, when t is 0, we're at 0, 0. Okay, it's vector 0, 0. When t is equal to 0, we're at 0, 0. Okay, when t is equal to 1, we're at 1, 1. When t is equal to 2, we're at 4, 2. Okay, so 1, 1. Okay, we're there. So our vector is, if we look at the point when t is equal to 1, we have a vector, okay, going this direction, okay, but we're going to put it at the tail. Okay, so 0, 0 had nothing. 1, 1, we have at the point 1, 1, okay, we have a vector going in the direction of x1, y1, right? So 0 did nothing. Okay, and then when t is equal to 2, we're at 4, 2. Okay, so that's 1, 1, 2, 3, 4. Okay, so when t is equal to 2, we're at 4, 2. So we're over here. Put the 2. Okay, so when t is equal to 2, we're at 4, 2. 2, 3, 4. Okay, 4, 2. So we have this vector here. Okay, but again, it's going to be the tail. Let's move that. Okay, so you get this field of vectors. Okay, so line integral of vector fields. Okay, line integral of vector fields. Oh, I always spell that backwards. Okay, fields. Okay. Let F be a continuous vector field defined by a smooth curve C given by a vector function R of t such that t goes from A to B. The line integral along or of f, the line integral of f along C is W equals the integral of C f dot dr, which is equal to A to B of f of R of t dot R prime of t dt, which is equal to the line integral of f dotted with t, which is the tangent vector. Okay, it's actually the unit tangent vector is t, ds. So remember, t was the unit tangent vector. And this is the dot product. So f dotted with, so that's the dot product as well. Okay, and this is the dot product as well. So it's f dotted with dr is f dotted with r prime of t dt, because that's what dr would be. Okay, r prime of t dt using the chain rule there. Okay, would be the derivative of r of t, r prime of t dt. Okay, and then this is the unit tangent vector. Okay, is t. Okay, so those are all equivalent. And what does W stand for? Oh yeah, W stands for work. This is work done by pushing a point, a particle, across this line, okay, this curve. Okay, so the work done in pushing this point, okay, is work. Okay, it's the work. Okay. Okay, so suppose F equals PI plus QJ plus RK. Okay, then what we would say, okay, is that the integral of C is equal to A to B of F of R of T dotted with R prime of T dt. Okay. Okay, which is equal to, this is FDR, sorry. C F dot dr is equal to this thing, okay, which is equal to A to B of PI plus QJ. Oh, what the heck happened there? Okay, QJ plus RK. Okay, dotted with X prime of T I plus Y prime of TJ plus Z prime of TK. Okay. DT. Okay, so let's dot these things. Okay, so dotting this, okay, we would get the following. We get P X prime of T okay, X prime of Ti plus Q times Y prime of Tj, okay, plus R times Z prime of Tk, okay, dt, okay, from A to B, okay, and so this thing, okay, going back to kind of like what we had talked about before, when we had something with respect to X, right? So you could break each of these into their individual components. This could be A to B of P, X prime of T. Well, I don't want to, yeah, I could do that. I dt plus A to B of Q, Y prime of T, J dt plus A to B of R times Z prime of T dt, okay? And so going backwards, we would say that this is equal to the line integral, right, of C P with respect to X. Remember the X prime here with respect to X, so dx, okay, plus, okay, and that'll be in the X direction or the ith direction, okay, plus the line integral over C of Q times y prime dt, which would be the line integral in the y direction. So this is dy plus the integral of on C of r in the z direction, dz. And I can bring this all together and say that's the line integral of p dx plus q dy plus r dz, and right, and that was equal to, okay, the line integral of this thing of f. Okay, so what is that? Well, that is the line integral of C of p. It was p I qj rk, pi plus qj plus rk ds, I believe, right? No, dr. It's dr. Okay, is equal to the line integral of, and you just separate them out, p dx plus q dy plus r dz. So if they're separable, we can just separate each of those components out. That's with respect to the ith, jth, and kth. Then it's just integrate on x, integrate on y, integrate on z. That's it. That's the proof there. Kind of what we're doing before in 2 dimensions. Okay, this is called a 3-dimensional line integral. Okay, 3-dimensional line integral. Okay, number 6. Number 6 says, find the work done by the force field excuse me. Okay, find the work done by the force field. Okay, F of xy equals x squared I plus, or say minus xyj in moving a particle, okay, moving a particle along the quarter circle, okay, r of t equaling to cosine ti plus sine tj, okay, where t is going from 0 to pi over 2, right? So we have this quarter circle, okay, and we're just using the parametric form of the circle, okay, because we want it to be a vector valued function here, right? So it's just a unit circle, but it's just the top quarter of it, okay, of the unit circle. This is 1, this is 1, okay, and when t is 1, I'm here, or when t is 0, I'm there. When t is pi over 2, I'm over here, so we're going this away, okay, for that thing, okay. However, that's really not what the force field is doing, because what's the force field doing? Well, you know, if we want to take all the points in here and look at how are they occurring, okay. Okay, I want to know what's the work done, okay, along this path. That's the work done along this path. I'm going to put this in a different color, right? So the work done along the path through the force field. All the work done along this path, but it's through this force field, okay? There's a vector field that's counteracting this thing. Okay. Okay, so I want to move along C, right? Find the work done by the force field and moving a particle along the quarter circle. Okay, so and again, what would this force field look like? Well, again, if we plugged in like 0, 0, we would get 0. Okay. If we plugged in like, I don't know, 0, 1/2, we'd still get 0, right? Wouldn't be anything where x is 0, we're going to get 0. Okay, so that's a nothing. Okay, but I'd have to deal with fractions, so I don't want to deal with fractions. But basically, it's going to look, let me put it in a different color. It's going to look like this here, and then it's going to look like this here. Okay, and then it's going to look like that here. And then it'll look more like so, and then like so, and then like so, and then this thing out here is going to look like this, and like this, and like this, and like that. Okay, so the green is the force field. What the force field is telling us to do. Okay, this F here. Okay, and so we're going to want to push the work through this force field, this vector field, okay, along the quarter circle. So what is the work? What's the work done? Well, the work is equal to the line integral of F dotted with dr, okay, dotted with dr. Okay. So this is going to be equal to F R of t. Okay, we're going to parameterize this on t. Okay, from A to B. And then that's going to be R prime of t dotted with R prime of t dt. Okay. Okay, so let's plug this in. It's with respect to t. T is going to go from 0 to pi over 2. Okay, what's f of r of t? Well, parameterize this thing. This is going to be, okay, and I'm going to use vectors, component notation to do this, because it'll just, for me, it's just, I don't know, easier to dot. I don't know what, however you want to think about it. We can leave it like this. That's fine. But we'll just leave it like this. To me, it's just in my brain, it's easier to look at it as components in component form than standard basis form. But whatever, we'll roll with it. Okay, so what is x in this case? Well, x is cosine t. What's y? Y is sine t, right? So this would be x squared I. This is just going to be cosine squared t I minus, okay, this is going to be cosine t sine t j, right? Dotted with what? Dotted with r prime of t. Well, what's r prime of t? Well, let's take the derivative. R prime of t is going to be negative sine t plus cosine, or negative sine t I plus cosine t j. Okay. So take this and dot it with negative sine t I plus cosine t j. Okay. Dot that. Okay. So dot component with component and then add them, right? So this with this, and then we're going to add them together. And this is dt, I believe. Yep. Okay, so this is going to be cosine squared t times negative sine t. So this is cosine squared t, negative cosine squared t sine t, okay, and then this is going to be plus, this is going to be negative cosine t sine t times cosine t. So this is negative cosine squared, look at that, that's another one, cosine squared t sine t, oh, okay, dt. I'm going to change colors. I don't like this color. It's just too hard to see on my screen. Okay, so this is going to be equal to, oops, too many equal signs, 0 to pi over 2 of negative 2 times the same thing, cosine squared t sine t dt, right? Okay, so I'm going to pull the 2 out. 0 to pi over 2. I'm pull the 2 out, but I'm going to do a u sub. Maybe I won't. Let's just do a u sub. Let's do a u sub here. U is equal to cosine t, du is equal to negative sine t dt. So there's the negative, and there's the sine t dt. Okay, so this is going to be 2u squared. Okay, so we want to integrate that, right? Integrate 2u squared. And we're going to get 2/3 u cubed. Okay, and what was u? It was cosine t. So this is 2/3 cosine cubed t, right? Evaluated from 0 to pi over 2. Okay, and then plugging in 2/3 cosine of pi over 2, that is 0, right? Yeah, that's 0. 0 cubed minus 2/3 times cosine of 0 is 1. 1 cubed. Okay, so this just comes out to be negative 2/3. Okay, and why is it negative? It's negative. Okay, it's negative because the field, the force field, impedes the movement along C. Okay, so it's negative work. Okay, so it's impeding, so the force field is going against. Okay, go back to my drawing. The force field here, okay, or the vector field, is impeding the work done, so it's a negative amount. Okay. Okay. So if I wanted to go along this curve, I'd have to go backwards. Okay. I'd have to go against the flow, okay, of traffic. Okay. Okay. So the force field is not doing positive work. It's not doing positive work. If it was doing positive work, it'd be going this direction, positive work, that direction. Okay, but because we want to go in the opposite direction of the force field, that's its natural bent, okay, then it's negative work. Okay, and you can see how this gets into fluid dynamics, right? Because you have to think about water in a tube, right? So think about water going through your tube, right? And what is it? Well, how do we deal with fluid dynamics? And the way we do is we think about all the molecules of water in the tube, and we treat it as if it were a force field, as if it were a vector field. That each of these molecules, maybe some of them, maybe we were getting a swirl here, right, up at the top. Maybe as it comes out, it puddles over here, and so we get a swirl over here, and we get these swirls there, and maybe along here it goes all of these points flow like that and comes over, and maybe we get a little whirlpool, a little back pull here. Okay, well, we could find a function that describes these these behaviors, model it as a force field, and it's like, well, what would it take for a marble to go? Well, how much work would it take for a marble to go backwards here? Well, we're going against the flow. According to the amount of force being applied, okay, you'd have to go in the negative direction, that amount of force, to get it back through the pipe, because the flow of water is coming out. And again, we think, okay, well, how is this a vector field? Well, again, you have to think, and we don't really think every molecule, because that would be insane. We just say, hey, can we approximate this, you know, like say that we have the mouth of a river, right, coming out, and what is the water doing? Is it going straight out? You know, is it bending to the side? Like what's the vector field that you know, is it coming out and is it going backwards? And so you get these little pools of, you know, and there are scientists that need to figure this out. Okay, you know, it's like, what's it doing? Is it coming out here and coming back, and it's building up the, you know, why do we continue to get beach here? New beach. This is new beach, right? Why is there new beach here? Well, it's because it's taking silt from the river. This is the river. And depositing it way over here. Okay, well, why is it happening? Well, it's because of fluid dynamics. And we can say, oh, well, maybe we'll take every foot and we'll measure it every foot. You know, you can't measure every molecule. We'll measure every foot or whatever, and we'll see what's happening, right? Take these measurements and see what's happening with the velocity of the water at that measurement, and then we say, oh, well, that velocity is going to give me a vector, and that vector is going to then give me a vector field, and then we just use computer to generate this vector field, and then we say, oh, well, maybe there's a nice equation that we can derive from that vector field. Okay, so that's it for me for today. 16.3 on Wednesday. Okay.
Bye. Thank you.
Thank you.